So we covered regular annuities, regular perpetuities. Okay, let's do growing annuities and growing perpetuities. So here, it looks really complicated, but it's not. Okay, so we mentioned previously that something like this is a regular annuity, right? So a growing annuity is very similar. This format just confuses people, but growing annuity looks something like this. So the first year, you might have a cash flow of $100. Second year, the cash flow starts growing at 5%, for example. So the third year, now the cash flow looks like that. Fourth year, cash flow looks like that. And the fifth year, it looks like that. Basically, if you're seeing this, from the previous year, it grows at 5%, 1.05. Okay. From this previous year, another 1.05. That's why it becomes 2. And from this year, another 1.5. So it's 3 and 4 and so on. Okay. So growing annuities are very similar, but just to make it clear, it ends after certain years. Okay. So growing annuities are very similar to regular annuities in that you have some kind of a constant cash flow occurring every year, but instead of it being of equal amounts, it grows at a constant rate. The payments actually grow at a constant rate. Okay? And it ends after a certain number of years. So that's the criteria. Cash flows that grow at a constant rate occurs regularly, just like an annuity, and it goes on for a finite period of time. Okay, it doesn't go on till infinity. Okay, that's a annuity. So this notation here looks confusing, but it's just $100 growing at 5%, 1.05, 1.05 to the second power, and this confuses people, but here we had year 5 and year 4, right? So year 5 and year 4 will be 5 minus 1, okay? If it started right here, okay? So, yeah, so just like the PVA formula, present value of an annuity formula, PVGA is present value of a growing annuity formula, okay? So we have two versions here, just like the PVA. I would say, you'll get the same answer, but the second one is easier to input into your calculator. Okay, so you'll put in your cash flow divided by, if you have a scientific calculator, I guess it'll look like this. But you gotta make sure that this thing is also in parentheses. You multiply it by this thing in the brackets. Okay, now that's you'll need more parentheses there, so you gotta practice. Okay, but the second version is, again, I think it's easier to put it into your calculators. Okay, and another thing, we still have this t and t plus 1 relationship. So just like back in your present value of annuity formula, present value of annuity formula, we're gonna check the first cash flow of the cash flow pattern. Okay, in this case, when does the first cash flow occur in this growing annuity pattern? Okay, in this pattern, the first cash flow occurs here. Okay, so we're saying if it occurs in time t plus 1, 1 is t plus 1. So if you do the math, t is 0. right? If you solve for t, and this tells you whatever number that you get will be expressed in times $0. Okay, so make sure you keep track of the timing of everything. Okay, so yeah, the solution to example 5 is already online. You should take a look. Okay, so yeah, you'll see in the solutions that the cash flow that's described here is a growing annuity. Okay, you see that you're gonna deposit money annually, regularly for the next 18 years. So it's not a perpetuity; it ends. You have a regular payment going for a finite period of time. It gives you the description of the cash flow. First deposit of 4,000. That is in year 1. So year 0, year 1, and then the amount will grow at 5% per year. The deposit that you're making will grow at 5% per year. So you know that it'll grow at 5% per year, and this will go on for 18 years. Okay, so you'll have some number here. You're given a rate of return of 6%, given the R. So you want to look for what's the value of the college fund today? Meaning, what's the value of everything today? So basically, PV of everything today. So since you know that this is a growing annuity, you will obviously use the present value of growing annuity formula. And how to do that is already online. Okay. Now, growing perpetuity. Okay, so yeah, growing perpetuity. So here, again, it's very similar to a regular perpetuity. We had regular perpetuity, right? Goes on forever. This was an example of a regular perpetuity. Equal amounts occurring regularly every year forever, right? That was the perpetuity. Now we have a growing perpetuity, so this would be an example. $100 the first year, but that amount increases, let's say again, by 5%. And in year 3, the pattern continues. The growth continues. Okay, and I'll just add another year. Year 4, it keeps growing, and that goes on forever. Okay, this would be a growing perpetuity, and there are problems where you'll have to solve for the present value of a growing perpetuity. So same thing, PVGP, present value of a growing perpetuity. Okay. So, how you apply the formula is the same. It's a little repetitive. Some people get it. If you pay attention and really think about it, you'll get it. Yeah, t and t plus 1. These are again time indicators. Okay, time indicators. Okay. What it says is, if you want to use this formula correctly, you'll first note when the first cash flow of that pattern occurs. Here, in this pattern, when is the first cash flow? Obviously, this is the first cash flow. And it tells you this first timing is what we call t plus 1. Okay? So if you do a little bit of algebra, if t plus 1 equals 1, it is 1, right? Then what's t? T is 0. So this tells you whatever number that you get by this formula, you get the value as of time 0, 1 period prior to the occurrence of the first cash flow. So the number that you get will be in time $0. Okay, that's all. So you're gonna, this is what I call the God example. You'll see that, yeah, I'll go over the setup real quick. Uh, God promises to give you $1,000 5 years from today. Every year after that, God will give you an amount that is 5% larger than the last amount. Let's put that on the timeline. God will give you $1,000 5 years from today. Okay, 5 years from today, year 5. And every year after that, it says every year after that. Okay, and 5% larger than the previous amount. So, second power, and so on. And God promises to make the annual payments forever. So we know that it goes on forever. So immediately you know that we're dealing with a growing perpetuity. Okay, the amount that grows constant at a constant rate, and it goes on forever, growing perpetuity. Okay, and you're trying to solve for the value of the promise today. You gotta read the question carefully. If the R is 6%, so R 6%, we want the value of the promise today. Okay, not what's the value of the promise in time 4. We're looking for the value of the promise today. So we're going to apply the PVGP formula, but since the first cash flow occurs in year 5, you'll get the value as of year 4, whatever number this is. So you got to take it back to time 0. That's the second step. And if you look at the solutions, you'll do something like that. Okay, you'll see. Okay, and here are a couple other exercises for the same problem. So same God problem. The only difference is when you receive your first payment. Okay, so this is a very useful exercise to see whether you understand the T and T plus 1 relationship. Okay, this applies to annuities and perpetuities. So you really need to know example 2, and it's a good exercise. Okay. Okay. Lastly, now we've learned different patterns, right? If you recall, we talked about uneven or irregular pattern. Example 1, where you had to, there was no formula. It's a multiple cash flow problem, but you have to apply the formula, the topic 2 problems, or topic 2 formulas, sorry, individually. How do you spell individually? Topic 2 problems, formulas individually, right? I think it was example 1. And then we talked about annuities, growing and regular. So these we had formulas for. And we had perpetuities, growing and regular, right? So these had formulas. And now we're talking about combination patterns. We can combine these with this, or this with this, whatever. Okay? So let me give you a couple examples. Suppose that you have this deal. Okay? So now I'm just color coding things. So basically, cash flow, the green cash flow, might be $100, and the blue cash flow might be $200. Okay, and we want to solve for the present value as of time 0 of this entire thing. Okay, so obviously it's a little bit complicated, but the idea here is once you're able to recognize the patterns, you can split these up into 2 different types. So for this example, we can say this deal, this entire deal, is equal to a 4-year annuity. So we have a 4-year annuity. So this part right here, 4-year annuity, plus a perpetuity, a regular perpetuity here. This part would be this part right here. Okay, so basically, the combined pattern, looks complicated, but if we split them up into two parts, they're easy to calculate. Okay, I hope you see. Yeah. So, to put this more formally, I'll come up with an expression. So what this is saying is we want the PV. I'll just call it the NPV, the net present value of everything as of time 0. To get that, we need to get the PV of the green cash flows plus the PV of the blue cash flows, right? Equals. So we're first taking care of the green cash flows right here. So here I'm just noticing that this looks like a regular annuity. It goes on for 4 periods only, constant amount, equal amount, cash flow, and occurring regularly. So it's a regular annuity whose first cash flow occurs in year 1. So here, no additional step necessary. You get the PVA as of time 0, and this is just the PVA formula, and you know that N is 4 because we have a 4-year annuity. Okay? And then we now have to take care of the blue cash flow pattern. We do it down here. Here, this one is a little bit more complicated. First, if we take a look, we know that it's a regular perpetuity. It goes on forever, and the cash flow occur regularly of the same amount. It's a regular perpetuity. So to get the present value, you first have to use the PVP formula, which is done here. Okay, so this is the PVP formula. It's a little. I'm just putting it in one step, so it might look confusing, but I'm just using the PVP formula, cash flow T plus 1 over R, right? In this case, it just happens that the first cash flow occurs in year 5. Okay, so the value that you get, whatever number this is going to be in time $4. Okay, same thing we've been saying, right? So this number is in time $4. That's why we have an additional step of discounting it back to time 0. Just like before, just like in the God problem, we discount it back to time 0. Okay? Yeah, so I'm just putting everything in one step, but that's what we're doing. We first get the PVP4, and then the second step is discounting it back to time 0. Okay? And we add everything up to get the NPV. Okay? Yeah, again, this, if you look at it initially, it might look a little complicated, but it's not. Basically, what we're doing is, if you think about it, let's say I give you 2 presents just for fun. Okay, I'll give you what is this? Apple pen. I think it was like $100. Then I'll give you an iPhone. I don't know how much it's worth. Maybe $1,000. Okay. If I give you these 2 as a gift in a bag or a worthless bag, then the total amount that you get, total value of the gift, is $1,100, right? That's easy to see. You just add the 2 values up. Here we're doing the same thing. It looks complicated. This is the Apple Pen part. You just have to calculate the value of the Apple Pen this way. And this will be the iPhone. iPhone will be the second part. And we took care of the value of the iPhone right here. And we're adding them up to get the total value. Just the calculations are a little bit complicated. Okay, good. So, yeah. Hold on. What is this? What is it? Yeah. So example 7 is an example of a combination pattern problem. You'll see. Let's take a quick look. Considering a project that will produce a cash flow of 4,000 for the next 5 years. So you should immediately see, or well, if you're used to it, first 5 years, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 4,000, 4K. So it's clear that this is a regular annuity, right? Starting in year 6, I'll use a different color. The pattern changes. The problem just tells you, right? Project is expected to generate a cash flow of 6,000 per year forever. Okay, so 6, 7, 8, 9, infinity. Now it's 6,000, 6,000, 6,000, 6,000, and that goes on forever, right? And we're trying to solve for the present value of all cash flows, present value of all cash flows, PV0 of everything, if the interest rate is 8%, if R is 8%. Okay? So here, now, that's why drawing the timelines is important. Here we know that the first cash flow pattern is an annuity. So we'll use the PVA formula here. You'll get the time value as of time 0 immediately because the first cash flow occurs in year 1. The second part, we gotta take care of the perpetuity part. And so we'll use the PVP formula, but note that the first cash flow of the perpetuity is in year 6, which means when you apply the formula, you'll get the value of PVP5. But we cannot add time $0 with time $5. So we're gonna discount this back to time 0 by doing this. This will convert the value of this perpetuity into time $0. Okay, you'll see it in the solutions. Okay, and example 8 is also on the exam.